Let's wrap that chapter up first. And what we want to talk about is delta G under standard conditions and K. You know, what is the relationship between delta G and where it ends up? And we're saying that delta G, can be strongly spontaneous, strongly non-spontaneous, or weakly. And if it's weakly, then we have more of a balance. There's more of a driving force going in both directions. Can you guys hear with that? Somewhat. You can move if you want, or I'll try to talk louder. But it turns out there is a relationship between delta G naught and K. And that is, if delta G naught is equal to, minus RT. I'm not going to go through the whole derivation of this. ln of K. And so here we can see how K and delta G are related, and we can see some numbers, when we do some calculations. So let's do some of the calculations here right now to figure out what K is. If K, if we solve this equation for K, we're just going to get that K is equal to, and I'll skip the algebra, it's going to equal E, we'll take the net, we'll raise both sides to E, and then we'll get E to the minus delta G naught over RT here. All right, so let's go ahead and get some values. So if we plug in delta G naught, we came up with this, like minus 200, or actually let's go plus 200 kilojoules. Delta G naught of plus 200 kilojoules, is that what? It's pretty non-spontaneous, highly non-spontaneous. And so let's go ahead and calculate the K value for that. And so we'll just plug it in here, E to the minus delta G naught over RT. And so here, that's going to equal E to the minus delta G naught. So it's going to be minus 200 kilojoules, or 200 kilojoules per mole. It should be kilojoules per mole, because it depends on how the reaction is written. Let's do that. Okay, that's my delta G. Then R. The R that we use is the thermodynamic one, 8.3145 joules per mole Kelvin. And then T, well, the temperature is going to be at, what's the temperature going to be at? At 298 Kelvin. It's going to be at 298 Kelvin because that's where our data is. So let's just do it for 298. If it's not at 298, then we would adjust it. And so what does that give us for a K value at plus 200? Well, one thing is the units don't work out. And so here I'm going to convert, let's convert kilojoules into joules. That would be the easiest. So I'll go with 1,000 joules per kilojoule. So, this here. I got 200 times 1,000 divided by 8.3145 divided by 298. That gives us 8.79. Let's go 8.79. When we deal with power functions, this is tricky what we do with the sig fig. Well, we're just taking this as exactly 200 kilojoules, so we'll just carry some extra digits here. But anyway, it's 10 to the minus 36. 10 to the minus 36, and K is the ratio of the products raised to their respective coefficients divided by the reactants. And so we see 10 to the minus 36, this is all denominator, and so it's all reactants. So it's kind of proportional to products over reactants. So we see we have all reactants here. It's a very small ratio. All right, if you go to plus 50 kilojoules per mole, what do you get for your K? Can somebody calculate it for me? Does somebody have it? I'm sorry? 0.98 is a little off. Yeah, that's going to be off. Significant. 0.98 should be quite a bit off. 1.02? 1.02 sounds off. Or maybe not. Did other people get around 1? Well, let me tell you, I know at 0, this one you should be able to calculate in your head. If delta G naught is 0, what is my K value equal to? 0. 0? That means, well, if it's 0, if delta G naught is 0, then my K value is 1. So if I see 0.98, just, yeah, maybe, but it's a lot. Did other people get about 1? At plus 50? You have a number?
2 times 10 to the negative 9.
2 times 10 to the negative 9. Give me some more digits. 2 point.
Oh my God, you're giving me.
Okay, 2.00 times 10 to the negative 9. And so one way of visualizing, this is not totally accurate because things don't necessarily go linearly when we have different coefficients. But one way of thinking about this is like a 1 to a billion ratio. A 1 to a billion ratio of product to reactant. Product to reactant. 10 to the minus 9. This still, if we have, if we treat this linearly, if we treat this as 1 billion parts of reactant to 1 part product, did much reaction occur? No. And so it's pretty much all reactants here. Very little product to form. But if the ratio is 1, yeah, then we have like a 1-to-1 ratio of product to reactant. And so in between here and here, so let's go to minus 50. At minus 50 kilojoules per mole, what is my K? Can you calculate this just for more practice? We want to make sure everybody gets the same number. And not just make a calculator error. Calculator errors are common. Just people miss key things or something else happens. So whenever you have a test, you always want to double check the calculation by just redoing it in your calculator. And see if you can get the same. Sometimes there's some kind of systematic error where you just keep repeating the same error, but sometimes it's some random error and you'll just catch it. So let me know when somebody has a number and then I'll write it down and then you can just check it. somebody have it? Keith, do you have it?
5.81 times 10 to the 8.
5.81 times 10 to the 8. So this is like 6 times 10 to the 8, which is close to 10 times 10 to the 8. And so this is kind of the opposite. It's almost, you know, a billion parts of product to 1 part reactant. So it's a billion to 1. Close to a billion to 1 ratio. If we have close to a billion to 1 ratio, then is there much unreacted reactant left? 1 out of a billion? No. And so this is pretty much all product, or starting to become that way. And if we get to minus 200 kilojoules per mole will give us a K value of what? Are you guys getting the same? Yeah, okay, good. And so at minus 200, what's the K value?
Calculator doesn't do that.
I'm sorry?
I think it overflows my calculator.
It overflows your calculator. That's the problem. You know, a lot of people think, okay, if I have a calculator, I don't have to know any math because I can just punch it in my calculator, right? But your calculator does a couple of things. Do you know how many digits your calculator carries? It depends on the calculator. But you should know how many digits your calculator carries. How many digits does your calculator carry, not anybody else's? Because it's your calculator that's going to make this error. What do you mean? Do calculators make an error? Do calculators make errors? Rounding errors. Calculators make rounding errors. And in this class, if you don't do things to prevent rounding errors, you could end up with the wrong answer. Let's say I'm asking you what is the percent reaction. You know, if I'm asking you what the percent reaction is, and your calculator doesn't carry that many digits, let's say it used to be 8 digits, you know, I think nowadays 10 digits is standard for, if your calculator doesn't carry, let's say your calculator only carries 8 digits, so I'm asking you what is the percent reaction here? So 1, 2, 3, 4, 5, 6, 7, 8. Let's say, okay, now your calculator has a 9th digit here, 10th digit, 11th digit. But your calculator only displays 8 digits. What's going to happen here? What's going to happen is your calculator is going to round this. Right? Your calculator is going to round this to 100%. And so it looks like we'll have 100%, but that's not what I was looking for. I was looking for what is the tiny bit, what is that tiny bit of reactant that's left over unreacted. You know, if we have 99.99999 etc. percent, I want to know how much reactant we expect to be left over. And if your calculator gives you 100%, then you'd have to say 0. There's nothing. But that's not what I'm asking. Let's say, you know, let's say the last digit was 6. And so what I was looking for is I was looking for 0.000004. 0.00004. In other words, 4 times 10 to the minus 9. 4 times 10 to the minus 9 parts left over. And your calculator does this and rounds it to 100, then you're going to be in trouble. Now your calculator can't handle certain numbers because they're just too big. But anyway, did somebody get this?
Yes, 1.14 times 10 to the 35th.
1.14 times 10 to the 35th?
Yeah.
Okay. When the numbers get especially large, then we have to just estimate them using this exponent, because eventually the number will either get, well, you'll see, one of the homeworks is like that, I think. Did anyone do the homework problem with the Boltzmann equation, where it asks you how many ways for mole? Did the calculator punch out the answer okay? Then maybe no worries about that. All right, so what was the reaction we did yesterday? The reaction we did yesterday was the 2 Cu pluses plus the tin 2 plus goes to 2 Cu 2 pluses plus the tin 4 plus. And the K value, you know, we came up with the K average, which is going to be the best because we don't know which one was the best experiment. Do you know experiment 1, experiment 2, or experiment 3, which one was the most accurate? We don't. So the best thing to do, since you don't know which one's most accurate, we'll just say we'll take the average, 1.486, which gives us a delta G value equal to what? What was the delta G value for the reaction we looked at yesterday? Oh, actually, we didn't finish it, did we? Huh? Oh, that's all right. Well, we'll finish it today. Does somebody have it? Let's see if I can do something about that here. All right, did somebody have it? So here we would just plug it into our equation here. Delta G naught is equal to minus RT ln of K. So that's the relationship that's observed between K and delta G. And so we need a temperature. What temperature do you think this is at? If the temperature is not specified, you assume it must be. It's got to be room temperature. It's got to be at 298. Now, are we under standard conditions? Are we under standard conditions? What are standard conditions? No, temperature is not part of standard conditions. What are standard conditions? 1 molar and 1 bar. Now, if you look at experiments 1, 2, and 3, were any of those at 1 mole? Well, the first one I did, which was like, I didn't even number it. I called it experiment. I didn't even call it experiment A, B, or C. It was the first one I wrote, which was just 1. That was 1 molar. Initial was the final at 1 molar. Was the final at 1 molar. So I know that, well, actually, this equation here, this is under standard conditions. This relationship is for standard conditions. Well, you know, was I at standard conditions for experiment 1? It was 0.100 molar. And the finals was like 0.03 whatever. Were those standard? No. Experiment 2, standard conditions? No. Experiment 3, no. The introductory experiment? Well, yes, initially, no at the end. No at the end. And so, is it okay to use this? This means standard conditions when clearly I wasn't at standard conditions. Can I use this 1.486 here? Is that okay? And the answer is yes. It's okay. Well, how can it be okay? Because those aren't standard conditions. And this one, I took the average. I took an average of 3 experiments, none of them under standard conditions, and then I'm going to plug it into this equation, which requires standard conditions. And so this is it. You know, this is why thermodynamics screws up a lot of people, because thermodynamics, people have to keep track of these things. A lot of people, they don't want to keep track of anything. They just want, give me the number, I'll plug it into the equation, it spits out the answer, right? But why can I use this equation when I'm clearly not under standard conditions? Should I use another equation? And so, what's going on here? The way we think about this is this. The driving force is, it depends on where your starting point is. You know, so for example, if the initial, let's say if the initial product to reactant ratio raised to the respective coefficients is 1.486, is there any driving force for change? So if your initial ratio is the correct equilibrium ratio, then there's no driving force for change because you're already at equilibrium. Why change anything to make this ratio bigger or smaller? It's already at the correct ratio. If your initial were not, goes back, you know, let's say your initial was 0 or your initial was infinity, then it's far from equilibrium, and then there's a driving force for change. And so, under standard conditions, this is what it means. It means that if in this case, all the concentrations, in fact, if under standard conditions, then that means all the concentrations have to be 1 molar. And so what we see is something like this. In 2, this goes to 1, actually I'll just say 1 molar, 1 molar, 1 molar, 1 molar. This is our starting point. And this would give us a Q or K value. This gives us our Q value. Our Q value is going to be, 1 squared for the copper times 1 for the tin divided by 1 squared for the copper on the reactant side times 1. In other words, our Q is 1. So if we're under standard conditions, this is what it means. All the concentrations, both reactant and product, even though we want to form product, all the concentrations have to be 1, because what this is our reference point. How long is your drive to school? Well, how long your drive to school depends on where you start, right? How big is your driving force? Well, how big your driving force depends on where you start. If you start, hey, I start at school. How long is my drive to school? My drive to school is 0 because I'm already here, right? So is there a drive? Do I have to drive? No. But if I'm far away, then I'm going to have to drive. And so what this is, what this is under standard, if we start under standard conditions, what is the driving force? So what we're doing is we're going to say, we're going to start under standard conditions. What's the driving force? Is there any driving force for change? Now, if KEQ, or I shouldn't say, if K is equal to 1, then hey, we're already at school. We're going to drive to school. We're already there. Is there going to be any driving force for change? No, because, you know, our starting point is 1, our ending point is 1. There should be no change, right? And so this is what this means. It doesn't mean that we have to end up at standard. This means our starting point is under standard conditions. How big is that driving force? And therefore, even though we had all this, we already know where the end point is. We know the end ratio's got to be 1.486. And so it's not 1, it's actually 1.486. Well, actually, I'm pretty close. I'm not that far away, right? And so is that going to be a big drive or a short drive? That's going to be a short drive, so that means my delta G is not going to be so big, right? So it's got to be a drive forward, so it's going to be negative. And my K is not so, right? Big or change. And so this is what this means here. Now, I can figure it out because I know I need to end at this ratio. So what is my percent reaction? Do I know my percent reaction? No, I don't. This is just going to be minus, what would you call that? I know I got to go forward because I got to make a bigger ratio here. I got to go from 1 to 1.48. And so this is going to be minus 2. And we don't know the 2y. Did you say? Y, we could use y, I use y and x for different things. When something goes to completion, I'll use y. If we don't know how much reaction there is, I'll use x. And so I'm going to just stay consistent with that. So I don't know how much. Whereas in the y, I already knew 100%, so I already knew what I could calculate y in my head, basically. And so this is going to be minus x, etc. You know, we set this up, and then we can solve for x, you know, using this ratio here, the equilibrium. Did anybody solve for x in that last problem? That we did? All right. Well, going back to this, so what is my delta G here? I'm not that far away. If I start at 1, I need to get to 1.486. What's my delta G for this? So here, you just plug it in. What's R? R is 8.3145 joules per mole Kelvin. What's T? 298 Kelvin. Ln of 1.486. Did anybody calculate? This should be pretty quick and simple, I would think. Nobody got it? You should get all right, it comes out, I'm going to convert it to kilojoules straight off. 0.981 kilojoules. Negative. Negative 0.981 kilojoules, is that a pretty big driving force? No, not at all. You know, if we're pretty far off, let's say, you know, our starting is going to be 1, standard conditions, and our end wants to be 10 to the negative 9. We're pretty far off, right? This is going to be like a plus 50 kilojoules in the reverse. Saying the reverse reaction should be favored. And so, anyway, that's the relationship here. Now, let's figure this out, because do we have to start at 1? No, we don't have to start at 1. We could start wherever we wanted. And in that last problem, that's exactly what we did. We had 2 copper pluses, plus a tin 2 plus. This is going to go to 2 copper 2 pluses and a tin 4 plus. And we set up the table, and at the equilibrium, we figured out what those should be, and then we plugged it into the K. Now the ratio between product and reactant at the end, no matter where you start, you could start at standard or you could start wherever else you want to start. You know, we can figure out where we're starting at by looking at Q. We know that the K is going to equal 1.486, and that was equal to what? 4x cubed divided by, what are the two binomials we have? This is a problem we left off with last time. Yesterday. 0.389 quantity squared. And then this one? 0.176 minus x. Now Kelly was able to come up with an answer for this. What did you come up with? 0.10014? Oh, okay. 0.0014? Oh, 0.10014. Okay, thank you. But that required some work to come up with this. What we have to do is we have to look. You know, x can be any number from 0 to, you know, when we look at it, x cannot be, let's say x cannot be bigger than this. So the biggest x we can have on this one is 0.176, because if x is 0.176, then this goes to 0, and we lose all of it. And the product's over reactant. And so can we end up with negative molarity of tin? Is it possible that if x is greater than 0.176, we'd end up with negative molarity of tin? So if somebody asks you to make some negative 6 molar sodium chloride, is it possible? No. And so we know that x has to be between 0 and 0.176 here. And then in this term is going to be 0.389 minus 2x. And so this is going to restrict it. Okay, 2x cannot be greater than 0.389, otherwise we run into a negative molarity. Negative molarities don't exist. The smallest molarity we can have is 0, nothing. And so that means that x has to be between 0 and half of 0.389. 0.1845. And so, yeah, this range is wider, so it has to be within this range here. And so we have to take a guess at a number within that range. And so we look at our K value. If you look at our K value is saying it's close to 1-to-1 ratio, product to reactant, right? And so maybe a good starting point is maybe half of this. Maybe we lose half of it. Does that make sense? For a reasonable first guess. The method of successive approximation is called the guess and check. So how did Kelly come up with this number? Well, you just guess. So I'm going to guess, and I don't want to guess too precisely. I don't want to guess like 0.13864, because it's too much calculator. And so I'm just going to guess it to 1. And so let's just guess it to 0.1. If x is equal to 0.1, then we end up with this. We end up with a K value. K should equal 1.486. Right? It's supposed to be 1.486. And so what we'll do is we'll plug in 0.1 here, 0.1 here, 0.1 here. And so I'll do this one first. So 2 times 0.1 is 0.2. And so we'll have 0.389 minus 0.2, and then square that. to a real calculator. Okay, times 0.176 minus 0.1 would be 0.076. So times 0.076. Then I'm going to invert this. And then times 0.1 cubed. Times 4. And I got a K value of 1.473. Close. You know, it's supposed to be 1.486. I got 1.473. It's pretty close. And should I guess bigger or smaller? And so I look at this. I don't know. Should I guess bigger? Well, it seems like I should guess bigger. I'll form more product. Right? If I guess a bigger number here, that means more change here. That means I'm going to lose more reactant and form more product. So I should guess bigger. Now, how much bigger should I guess? Well, I'm going to guess, well, not that much bigger, but I still want to keep the number of digits small, so I'm going to guess 0.11. And that way I don't have to mess around with my calculator too much. And so I'm going to go 2 times 0.11 gives me 0.22. Okay, minus 0.389. It's squared anyway, so it doesn't matter. Square that times. All right, now I'm going to go 0.11, so I can do this in my head. And that's going to give me 0.066. 0.066. Okay, I'm going to invert that. Oops, I think I hit the key twice. I'll just redo it. Or actually, you guys should do this because you guys should get practice doing this quickly. So what does it come out to? All right, I'll do it too. It doesn't take long. You know, I just screwed up with the calculator because this calculator I'm not used to. So 0.22 minus 0.389, I'm going to just redo it. Squared times 0.066 equals, invert that, times 0.11 cubed times 4. And I get 2.824. Anybody else get that? And so now that's way, way too big, right? Way too big. And so what I want to do is I just want to go up a little bit. You know, I want to go one part up in about 100. And so, you know, if I look at this, I need to just go about one part up in about 100. 10th, 100th place. And so I'm going to go one part up out of about 100. So I'm going to go to 0.101. Let's try that and see if that does it. And so 0.101 times 2 is 0.202 minus 0.389 equals that, square that, times 101 minus this is 0.65 equals, invert that, times 0.101 squared, or not squared, cubed, so times 4. 1.813. 1.813, still way too high, right? And so here I'm at 1.4, I just need to go 4.8. And so let's go again. I'm going to go 0.10001. It's probably still too big, huh? What do you think? 0.1001. Let's just try it and see. And so times 2 gives me 0.2002 minus 0.389, square that whole thing, times, can I do this one in my head? This is going to give me 0.0759. Invert that times 0.1001 cubed times 4. 1.48 1.482. Ooh, so close. 1.482, just so close to that. I want to go for the 6. But, you know, when do I stop? Well, when you stop is this. Look how many decimal places I have here. I have 3 decimal places, so sig fig rule says I'm only allowed 3. So I could stop at 4 here. That's possible, but let's see if you can get it a little bit better. I'm going to go to 0.100. I just want to go a hair bigger. Just a hair bigger. So, well, let's see what happens if I go 0.1001. What? Give me a guess. It's a hair bigger than this. 4? All right, let's go for 4. Just try it and see what happens. I mean, it's just a guess. If it's too big, we'll go down. If it's too small, we'll go up. All right, so we're going to go for that, 0.10014. This one, I should probably do it in my head. 2 times that is going to be, that's not hard, 0.20028 minus 0.389. Square that times, okay, this one I'll do parentheses, so I'm going to use my parentheses now. Times parentheses 0.176 minus 0.10014, close parentheses, equals invert times 0.10014 cubed times 4. Oh yeah, 1.527. Is that, did you get that, Kelly? What did you get? You got 1.486? All right. You got 1.486? Then I probably miskeyed it then. You got 1.486? We're good. And so this is our best x value here. And we're going to use that here. And so what we'll do is we're going to calculate the concentrations now here. And so what's going to happen is, you know, we started at 0.389. This is a molar. These are all molar. I don't include the units here. There's a reason I don't include the units. I'll talk about that soon. But this is going to be 0.389 minus 2x. And so let's go 2 times that is going to give me minus 0.20028. We'll carry some extra zeros there. This will be 10. That's going to give us 2. That's 9 from 2. This goes to 7. This is going to be 8, 8, and 1. Now, how much of a reaction do we have? When we look at this, we started off with 389, we lost 200. What percentage is that? So if we start off at 389 and we lose 200, let's figure that out. I'm just going to do 0.20028 divided by 0.389 equals times 100. I don't have the equals. This is 51.48% reaction. There. And so about 51% of it reacted. This is how much I'm going to have left over, unreacted. And so about 49% unreacted, 51% reacted. So not all of it reacted. And so I didn't know what my x is. Now I know what my x is. Minus 2x is 0.200, and that's about 51% reaction. Now over here I started off with 0.176. I'm going to lose x of that. And so this concentration here is going to be 0.176 minus our x, which is 0.10014. And so what does this come out to? 0.17586 molar. Here, what was the percent reaction of the tin? Well, we started off with 176, about 100 of it reacted. Oops, sorry, 0. And so let's go ahead and do that. I'm going to just take the change, which is the x here, 0.114, divided by the initial, 0.176, times 100. And this was about 56%. It was about 56%, 56.89% reaction. And this is because, which one was the limiting reagent in this one? Was it the tin or the copper? The copper. If the copper is our limiting reagent, then what we say is, well, this reaction gave us about 56%, 57% reaction. Okay. I'll erase that. And then 2x here is this. 2x is going to be 0.20028 molar. And then x is going to be 0.10014 molar. And so what I have is this. I started off at these, this is 0 and this is 0. This is all molar. I started off with this, and what I was able to do is I was able to predict how much reaction occurred and what the final product mixture is going to look like. And this is the final product mixture because this is the end of the reaction. Once we hit the equilibrium or the end, there's no further change. And so this is where it's going to stop. And this is the maximum amount of product I'm going to form from this. I'm only going to get 56% reaction of the tin. Does that make sense? Well, anyway, let's do this now. Is there a way to double check my calculations? And there is a way to double check your calculations. We should double check all our calculations if it's possible. This is will show if we made some kind of error. And so our double check involves doing this. Our double check involves calculating K based on the concentrations we have here. And so calculating K based on the equilibrium concentrations that we just calculated, we have 0.20028 squared, because that's going to be the copper 2, times 0.10014 divided by 0.18872 squared divided by 0.07586. I carry these extra digits. Why do I carry the extra digits? I carry the extra digits for this double check, because if I round things off, then my K is going to be off. And if I round things off and my K is off, then I don't know, is my K off because of a round off error, or is my K off because I made a mistake? Well, if you carry extra digits, then you eliminate one of those possibilities. If you carry extra digits, you can say, okay, it's not because of rounding, it's because I made some more serious error. And so I should go back through and double check everything. And so anyway, let's see what our K value comes out to. This product to reactant ratio should be this should be 1.486. Let's see what it comes out to. Hopefully I didn't make a serious error and it comes out. And so 0.228 squared times 0.10014 divided by 0.18872 squared divided by 0.07586, and I get 1.48667. What do you think? Is that due to round off? Because we had it down to 1.486, I think 0, or maybe, I don't know. What was it? Was it in that last, when we did the X calculation, did it come out to 1.4860, Kelly, or was it close? Oh, that's all right. I would have tried to get it even closer, but we'll survive with this one. Anyway, this is close. Sometimes it's going to be off a little bit due to round off. I mean, we can't carry all the digits in the calculator. It's too much hassle. And so we're going to have some round off. So the numbers might not match. But as long as they're pretty close, we're good. All right, so this is how we're going to do Chem 1B stoichiometry. With Chem 1B stoichiometry, we need a K value. There are different ways we can get a K value. One way we can get a K value is by doing experiments. Experiment 1, experiment 2, experiment 3. Measure the concentrations and then calculate the Ks. Another way we can get the K value is by determining delta G. And there are multiple ways of determining delta G, right? And then we can get the K value based on our delta G value. We can also get a delta G value based on the K value. If we know the K value, like 1.486, then we can calculate the delta G value over here. This says it's spontaneous. Yes, it's spontaneous. There's driving force, but how big is that driving force? When you look at this, did we have 100% reaction? Even though we had a driving force, delta G was negative. And so just because delta G is negative, can we assume 100% reaction? No, because when we look at it, it's not such a huge driving force that we have here. All right, that's delta G naught and T. Now we can change the temperature. If we change the temperature, that's going to change the driving force as well. We could try coupled reactions. If we try coupling reactions, that can change the driving force. But there's a couple of other things we could try, and that is we can go non-standard. Non-standard conditions and delta G. If we go non-standard conditions, then it turns out that we can just take our delta G under standard conditions and adjust it. Our delta G under standard conditions has a starting point of what? Our starting point is, if we're thinking about the drive, our starting point is going to be what number? One. When delta G under standard conditions means it's 1. What we're going to do is we're going to adjust this here. And so the way we adjust it is we go plus RT ln of Q. And so our starting point might not be 1, it might just be Q. Well, Q could be 1, but Q could be any starting point, whether it's 1, 0, infinity, or whatever else. And so here we're just going to adjust it for where we're starting out. We might not be starting. We might be starting at 1.486. If we're starting at 1.486, then is there any driving force for change? In that last reaction, if we started with a ratio of 1.486 and we're supposed to end at 1.486, then there's no driving force. There should be 0 driving force. And so what Q is, what is Q? Q is the same thing, the product to reactant ratio, but starting at 0. Right. And so we could do some calculations here under non-standard conditions. So if I think about Q, so it's going to look like this. Q is kind of proportional to the product to reactant ratio. So if I increase the product concentration, is that going to increase my driving force for forward reaction or decrease? What do you think? If I have lots of product in there, then it should decrease it. And therefore, if the product concentration goes up, Q becomes bigger. If Q becomes bigger, this term becomes more positive. If this term becomes more positive, delta G becomes more positive, which means driving force goes down. So if I want to increase the driving force, I don't want to increase the product concentration because my delta G is going to go up. What I want to do is I want to increase the reactant concentration. If I increase the reactant concentration, then this number becomes smaller. And a number less than 1 will give me a negative ln. And if I get a negative ln, that's going to decrease my delta G. And so this is going to result in a decrease of delta G. So what I want to do is, if I want to help improve the driving force, I could just increase the concentration of the reactant. Or I could decrease the concentration of the product. If I decrease the product concentration, that's going to help my driving force as well. And so this gives us an alternate way of doing it. And so we're going to do a simple one first. Now, one thing that we should note is this. One thing we need to note is that if we're dealing with gases, so far I've just been dealing with solution, but if we're dealing with gases, are we going to use the molar concentration or what? We can use the molar concentration, but let's talk about K, C, Kp, and Keq next. Kc is the ratio of concentrations. And so we'll come up with as a generic equation AA plus BB plus CC. This is going to react to form GG plus HH plus ... This is where little a, little b, those are the coefficients, A and B are the reactants. And so this is going to be the concentration of A raised to little a power, products over reactants. So this will be the concentration of G raised to little g, concentration of H raised to little h. So we just put all the products there, divided by the reactant concentration, AA, BB, ... And so C just means the concentrations. Well, it turns out that pressure is related to concentration. You know, if we think about a gas, and gas pressure, P is equal to nRT over V. N over V is just the molar concentration, moles per liter. And so the pressure is equal to the molarity times RT. And so the pressure and the concentrations are going to be related. So what we can do, and they're related just by this constant, RT. And the temperature doesn't change. So this should be constant. And And so what we could do is we could do this. We can come up with a Kp value like this. A Kp is going to be just the same ratio. Since pressure and concentration are directly proportional, we can express this ratio in terms of pressures instead. So we could go the partial pressure of G raised to little g, partial pressure of H raised to little h, dot, 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 divided by the partial pressure of A to the A, partial pressure of B to the B, dot, dot, dot. And then we can relate the two. If we know that the pressure is equal to the concentration times RT, then what we get here is this is going to equal the concentration of G times RT, and the whole thing is going to be raised to the little g power. And then over here, we're going to get the concentration of H times RT. That gives us the pressure raised to the little h power, dot, dot, dot. And then we'll have the concentration of A times RT, the whole thing raised to the A. And then B RT raised to little b, dot, dot, dot. Now, what we're going to do is we're going to factor out the RTs in both the numerator and the denominator. If we factor out the RTs from both, then we see that Kp is equal to Kc times RT. Now, RT in the numerator will be G plus H plus dot, dot, dot. And then RT in the denominator will be RT A plus B plus dot, dot, dot. And so when we think about this, this is the sum of the coefficients in the products. This is the sum of the coefficients in the reactants. And so we're going to simplify that. We're going to call it Kc RT to the delta N of gas, where delta N of gas is given by this equation. To hit that. Delta N of gas is just equal to the sum of the moles of gas in the product minus the sum of the moles of gas in the reactants. And so basically it's going to be the change. Moles of gas. And so we could get, rather than using concentrations for gases, we could use pressures if we want, or we can just use concentrations because that would be the ratio. But when we go into the thermodynamics, these are the ratios that were determined, from empirical data. These are the ratios that we get from experiment. For example, where did that 1.486 come from? That 1.486 came from experimental observations, and that's where a lot of K's come from. But if we're going to derive K from thermodynamics, then what we get is KEQ. This is the thermodynamic equilibrium constant. And so what I need to do is I need to modify the equation I had up there earlier. Delta G naught is equal to minus RT ln of KEQ. Now what is KEQ? Is it a KC or KP? Well, it depends. For all solutions, then KEQ is equal to KC. If we're dealing with all gases, then KEQ is equal to KP. If we have a mix, then we get something like this. We get KEQ will be a mix of concentrations and pressures. Now, there's one more thing, because now we're going from experimental back to theoretical. And the one more thing is this. So let's take a look at some of these. So for the copper, actually I should just do it on the overhead. For the copper reaction that we just did, Kc is equal to Keq. If we do a reaction of all gases, let's say I do this one, NO gas plus NO gas gives me N2O2 gas. Oh, is it redox? No. This is just a reaction here. What can happen? Here, Keq, it's all gases, so Keq is equal to Kp. Kp is just equal to the partial pressure of the products of the partial pressure of the reactant. So the partial pressure of N2O2 divided by the partial pressure of NO would be squared. If I have a mix of things, let's say aluminum solid plus 3HCl aqueous gives me 3/2 H2 gas plus AlCl3 aqueous. Then I have a mix of gases and aqueous solutions. So Keq will be a mix. And so if I do the Keq for this one, I'm going to get Keq is equal to, okay, since we have a gas here, it's going to equal the partial pressure of hydrogen gas raised to the 3/2 power. Then it's going to be times the concentration of AlCl3 divided by, now what do I do with aluminum? Should I use the concentration or the pressure of aluminum? What we do with aluminum is this. Aluminum's interesting because in this reaction, let's say I started off with 6 molar HCl. The HCl starts to react with aluminum. As the HCl reacts with aluminum, its concentration goes down as I'm losing HCl. Now, if I have chunks of aluminum, the chunks of aluminum start off as 100% aluminum, pure aluminum. If I eat half of my aluminum away, did its concentration change? Okay, let's say I have a pound of gold, pure gold, and I gave half of it away, so I only have a half a pound. Now, the question is my gold now only 50% gold? Did its concentration change, or is it still 100% gold? It's still 100% gold. If you have a gallon of milk and you drink half of it, is it now half as concentrated, or is it still the same concentration? It's still the same concentration. Now, when we think about reactivity, if you think about reactivity is going to change with concentration. If something's super concentrated, it's usually super reactive. The more concentrated it is, the more you better watch out because the more reactive. Like 15 molar nitric acid versus 1 molar nitric acid, I'm going to treat 15 molar nitric acid much more carefully, right? But if I pour half my bottle of nitric acid out, now do I have 7.5 molar, or do I still have 15 molar? I still have 15 molar, I just have half as much. Well, when we have a pure solid like this, if I eat away half of it, it's not going to change its reactivity because it's still 100% aluminum. And so what we do here is this. We're going to omit pure solids, and for the same reason, pure liquids from our K expression. I'll talk about why that is in a minute. And so we don't bother with aluminum, and instead we're just going to go straight to the concentration of HCl and then cube it. And so there's no aluminum in here because its concentration isn't going to change, and therefore it's not going to change its driving force for reactivity. Now, we could, pure aluminum has a certain number of moles in a liter. How many moles of aluminum can you fit in a liter? Well, that would be its concentration. We could do that. Well, just like pure water. You know, pure water, if I dump half of it, it's still pure water. But it does have a concentration. Do you know what the concentration of pure water is? 55.5 moles. We have 55.5 moles of water into a liter. Therefore, pure water is 55.5 molar. But does it ever change? It never changes, so you don't really use that number much. Now, now it turns out when we dig deeper into thermodynamics, it turns out that we don't use this. Deeper into thermodynamics, KEQ is not KC, it's not KP, it's something else. KEQ turns out to be the activities of the products. So it would be the activity of G raised to little g, activity of H raised to little h, dot, 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 divided by the activity of A raised to little a, activity of B raised to little b, where A is the activity. Activity, this is chapter 14. Can somebody just remind me of what activity is? Probably not. I don't think anybody can remind me. Because either it wasn't really covered in much depth or you never used it. Well, what activity is, it's the effective concentration. Versus the stoichiometric concentration. Sometimes what we see is that the effective concentration is less than the stoichiometric concentration. Do you know why? One of the examples in the book is given by certain carboxylic acids. Tend to orient themselves. So if you have a carboxylic acid dissolved in water, it should be independent of other carboxylic acids. But what can happen is this, and the big example in the book is with like HF or that type of stuff. But what can happen is if these two align themselves like this, where R is the rest of the carboxylic, it could be any carboxylic acid. What happens is the hydrogen bonding interactions are perfectly aligned. Now this oxygen is going to be hydrogen bonded to this hydrogen here. This oxygen is going to be hydrogen bonded to this oxygen. Now, hydrogen bonding interaction is kind of strong, so let's say it's 25 kilojoules. All of a sudden now, how many kilojoules are holding these two molecules together? Well, if each one is 25 kilojoules, now we got 50 kilojoules holding these two molecules together. 50 kilojoules is starting to approach the energy of a weak covalent bond. And so this is like a couple, and they're kind of stuck together. And so if we got two acetic acid molecules, the two acetic acid molecules like to do their own thing, and then all of a sudden they're aligned right, and they got 50 kilojoules holding them together. They're not going to be doing their own thing anymore. They're going to act as one unit. If they act as one unit, then what happens is the effective concentration goes down. This is especially important in colligative properties. This is called dimerization. So we take one and we make two. That's dimerization, and sometimes these dimers are held together quite strongly, sometimes they aren't. If we think of dimerization, the great example would be DNA, double-stranded DNA. Does that act as two separate units, or does that act as one DNA? Is that right? Is there two molecules in DNA or one molecule? Somebody tell me. Is it 1 or is it 2? And the two have just dimerized. What is it? Uh-huh. Is it 4? Oh, 4? Okay. Then I don't know. Actually, I don't know. That's why I'm asking you. I'm asking you because when we think about it, we just think about it as being one unit, right? But it's all stuck together. Maybe it's not one unit, right? But it behaves like one unit, or it seems to behave like one unit, right? Well, the same thing like this. This is supposed to be 2 molecules, but it's going to behave like one molecule because now it's got like 50 kilojoules worth of energy holding it together. Well, that changes its behavior and is going to change its effective concentration. So if we were thinking about 1 molar, well, there's still 1 mole of molecules in there, but as far as colligative properties, it doesn't behave. It behaves more like it's a half molar. But anyway, this is it. And so we should be using activities. Now, when we use activities, the activities are going to be like this. This is where the activity of a solution is about equal to its regular concentration. The more dilute it is, the more accurate this is. The more concentrated it is, the more problems we have with dimerization. You know, if there are very few acetic acid molecules or whatever else in solution, they really aren't going to find each other. And so the activity of gases is about equal to the partial pressure. The same thing here. The activity of a solid, the activity doesn't change of a pure solid. The activity of a solid is 1. And the activity of a liquid, pure liquid, is 1 here. So, and then we pretty much get the same answer as what I said before. We ignore the solids and liquids because those are just 1. All right, now finally we're going to do this one, delta G. We can use delta G to alter the driving force. And we can also use temperature. And so let's take a look at delta G and temperature. So we're going to go non-standard and change the temperature. Okay, so normally we do this. Normally we do, in our normal calculation, where do we get delta G naught? What's the easiest way of determining delta G naught?
Delta G of products minus delta G of gas.
Yeah, we use appendix D. And when we use appendix D, unfortunately our temperature is fixed at what? If we use appendix D, the temperature is fixed at 298. Well, if our temperature is fixed at 298 because of appendix D, that means our delta G will be fixed also. That's going to mean that this must be at 298 Kelvin because our delta G naught is at 298 Kelvin. And then this is going to be plus RT ln of Q. We'll just plug in Q from the earlier equation that was given out. And so we could calculate delta G under non-standard conditions at 298 Kelvin pretty easily. Just plug in the numbers. But what if we want delta G under non-standard conditions at a temperature other than 298 Kelvin? Then what that means is we have to determine delta G naught at another temperature. And so this is what we do. When we want a T not equal to 298 Kelvin, then you have choices here. If we want a temperature not at 298, choice 1, we could just break it up into separate calculations. Okay, first calculate delta G naught at T, whatever the desired temperature. Then, 2, we use that delta G naught in this equation. So this will be delta G naught at temperature T plus RT ln of Q. Plug it in there. Some people don't like 2 calculations. Some people would like to combine the equations so that they only do 1 calculation. And so, alternatively, we can combine the equations to do just 1 calc. And so that means we'll have to do some algebra combining the equations. And so what are the equations that we're going to combine to come up with this? Well, we don't have to do that. Okay, this is for solving for delta G. This is easier just to do it separate. Now solving for T, if we want to solve for the temperature at which we'll get a certain delta G, and so solving for T, that becomes a little bit more complicated because here we know that delta G is equal to delta G naught, right, plus RT ln of Q. So if we want to solve for T, let's say we want delta G to go from positive to negative, and so we set it to 0. And so we might set delta G to 0, then we try to solve for the temperature. So the problem is this. I can calculate delta G naught easily if I know the temperature. Right? There's no problem with that. But if I don't know what the temperature is, how can I solve for my delta G naught when I don't know what the temperature is? Is there a way to do it? And so, in a typical calculation, how do we solve for this?
Delta HF plus T delta S.
Yeah. So we'd probably go like this. Delta G is equal to delta H naught minus T delta S naught plus RT ln of Q. We might do something like that. And then what do we do? We'd probably factor out the T over here. And so that gives us a delta G is equal to a delta H naught all right, what we'll do is we'll just do this. We'll factor out the T, so we'll go plus a minus delta S naught plus R ln of Q times T. So, and then we go, what? We would go, this would be delta G minus delta H naught is equal to T, divide by both sides here, maybe go R ln of Q minus delta S naught, right? And then maybe that allows us to solve for T, etc. And so what we'll do are things like this, but why would we want to be able to solve for T? Why we want to be able to solve for T is because we want to do something. And so what we want to do is something like this. And this is what I'm going to have you do. I'm going to have you do some calculations. The first calculation is this. We're going to go H2O to H2O gas. You know, delta G at 298 under standard conditions. Delta G naught at 298 Kelvin under standard conditions is greater than 0. And so what we want to do is we want to make this spontaneous. All right, the first one, we're going to repeat my calculation. We're going to change the temperature. We're going to make it spontaneous by changing the temperature. Two, we're going to try to make it spontaneous by keeping the temperature at room temperature and going non-standard conditions. Three, we're going to change the temperature and go non-standard. And so after you figure out number 2, I'll tell you what the non-standard conditions for. And so, in other words, what we're going to do is we're going to boil water by heating it up. 2, we're going to boil water by going non-standard. And 3, we're going to boil water by going non-standard and altering the temperature. And so you're going to need some data for water. Let me put that up on the board, and then we'll have this as a worksheet type problem. But we'll do it on flashcards so I can check it as we go along. All right, we'll take a break and then we'll just start this worksheet problem. I'll put the data on the board when I get it. All right, here's some flashcards here.